I'd like to start by thanking the organizers for putting together this wonderful program and letting me speak here. It's always great to be back in Bonn. So I should start by clarifying that this is not exactly the title that I put in my abstract. I slightly changed it. Most notably, I inserted the word sharp. Because earlier in the trimester, I learned that nobody cares about multiplicative constants. This is very different in this talk. I really care about multiplicative constants, and I want to have the sharp constant. Okay, so that's what I mean by sharp.
And why nobody cares? I know.
If the constant is between 1 and 2, and you care about running time of an algorithm, then
Don't start the fight.
But I really want to know what's the sharp constant. Okay, so let's get started. This is my table of contents. So I'm going to start out by an introduction. This is a very gentle talk, so everybody is supposed to be able to follow. I apologize in advance for those who will be bored for parts of the talk. And after the introduction, we're going to talk about a key tool for the proof. Those are 2-point inequalities. And then we're going to talk about a little bit of computer assistance. So what's the isoperimetric problem? We're talking about subsets of the Hamming cube, so 0, 1 raised to the power n. And I want to measure the size of such a subset by simply counting the vertices contained in the subset and normalizing. Okay, so that's for the rest of the talk going to be my normalization. And the basic question is with the volume of A, so this is what I view as the volume, so simply the normalized count of vertices fixed, how small can I make the boundary of a set, right? So there's two unexplained terms here, small and boundary. So we need some notion of boundary. What is a notion of boundary? Well, the first that may come to mind is the vertex boundary, right? So what's a vertex boundary? There's two naive ways of defining this. So either you could look from the inside of the set and count all the vertices that have a connection, so I have an edge connecting it to the outside, or you could do the same count from the outside. Here I want to go with the inside one. And so let's fix the volume of a set and ask simply, well, what's the answer to this minimization problem, right? And obviously this has been studied. This is interesting for many, many reasons. And the answer is more or less the Hamming balls. So let's take one example family of Hamming balls of roughly half the volume. So what do I mean by a Hamming ball? It's exactly what you would think it would be. So you just take the set of all bit strings of length n so that it has less than or equal n divided by 2 ones in it. And now we can compute what's the volume. The volume will be 1/2 as n gets large. What's the volume of the boundary measure? There's various ways to compute it using the essential limit theorem or just manually. And you can work out that it's this funny constant that also pops up in the central limit theorem, should be familiar, at the n to the minus 1/2. And the remarkable thing about this is that it goes to 0. So if I'm interested in proving inequalities that are independent of n, then I am not going to be successful to get any interesting lower bounds that are independent of n. So this is not the right notion of boundary that I want to consider. So what's another notion of boundary? Instead of counting vertices, I could count edges, right? So let's start counting edges. I want to introduce this notation. I know in a talk you should introduce as little notation as possible, but this is one of the only pieces of notation I'm going to really need. So what is HA of x? It is simply for those points in x, it is going to count the number of edges that go to the outside of x, right? So similarly, we could be looking at the same situation from the outside, and if we take expectation, then no matter if we take HA or HA complement, we get the normalized count of the total boundary edges. So we're just counting all the boundary edges. And this is no longer minimized by Hamming balls. A different kind of example comes in here. So let's look at codimension k cubes. What is a codimension k cube? I take all the bit strings of length n and I fix k coordinates and I set them equal to 0. This is a subcube, right? Again, I can compute what is the volume, it's 2 to the negative k, and I can compute what is the edge boundary measure, and it is going to be 2 to the minus k times k, and I want to write this in this funny way, changing variables with the volume, and this function is a function we're going to see many times over. So what we have here is the classical isoperimetric inequality for the humming cube. So the edge boundary measure is always bounded from below by this funny logarithmic function, and since there's this symmetry with the complement, we also get a lower bound when we take 1 minus x. So we can, if the volume is bigger than 1/2. So the question is basically, so there's some deficiencies here, right? Like, so for instance, these are not all sets have a volume that can be written in this way. And also, so I would like to know what happens for other sets, right? So for sets that are not co-dimension co-cubes, for sets that are not of this volume. And so in general, I could ask what is again the answer to the minimization problem, and the function that comes up is the edge isoperimetric profile. So for every x, it's my fixed volume. I want to minimize over all n and over all sets of that volume. What is the edge boundary measure? Okay, and this is a problem that has been solved by various people in the 60s and 70s, and is a beautiful answer. It doesn't look so beautiful if I write it up as a formula, but you take the volume of your set, it's always of the form k divided by 2 to the n, and then you compute this expression here. And you can plot this, and what you get is this beautiful blue fractal plot. And what I've drawn here below is this orange plot, which is exactly the function that you get from only considering subcubes of size 2 to the negative k. So a natural question that you might ask is, well, which sets give rise to these intermediate points on this plot, right? So what are the extremizers for other volumes than 2 to the minus k? And they actually also take a really simple shape. They're just, you take a certain volume and you start ordering the vertices of the hypercube in lexicographic order, and you take the first that many as you need for to achieve that volume. And this is really easy to do on a computer also, because the lexicographic ordering just happens to be the way we count integers, right? So if we write integers as binaries, then the ordering of the integers is exactly the ordering of binary strings in lexicographic order. So this problem has been exhaustively studied. And so all I care about what is the exact answer to the minimization problem, then I'm done here and we can all go home, talk is over, right? Except I'm not quite satisfied yet. So there is some deep connection between isoperimetric inequalities and any inequalities on the hypercube with inequalities on the Gaussian space. So I want to tell you a little bit about the Gaussian space. So let's say Rn with a special measure, and this is your familiar Gaussian distribution function, and if we take this as a measure, we can compute a boundary measure. This is also a familiar formula that we all know. So if you do this formula for the Lebesgue measure, and your set A is nice enough, then this is exactly going to give you a useful notion of boundary, such as a lower dimensional Hausdorff measure. So for nice sets A, you can also write this as expectation of the absolute value of the gradient of the characteristic function, right? Whatever that means. If A is not such a nice set, you can make sense of it. So this is a problem that was studied by many people in the 70s, 80s, and 90s. And the upshot is that we have a Gaussian isoperimetric inequality. So again, we're going to ask for a fixed volume of A, Gaussian volume of A. What is the least possible boundary measure? And if you think about it a little bit, it's very plausible that you should put in half spaces. And so the conjecture should be that half spaces minimize this problem, and indeed this is what you can prove. So And now you can just compute what is the boundary measure for a half space. And if you do that, this funny function here comes up. So let's look at the cumulative distribution function on Gaussian space. This is a monotone increasing function which has an inverse, and we can plug the output of that inverse into the Gaussian distribution function again, and then we get this funny function I. This is the Gaussian isoperimetric profile, and this is important because it gives you the answer for this Gaussian minimization problem. Okay, so this is an inequality that's been known for a long time, and this function has a very special property. Its second derivative multiplied by itself gives you -1. So it solves this funny second order differential equation, and at the endpoints 0 and 1, it gives you the value 0. Okay, this is a typo, this should be 0. And this is the plot of this function. So, what does this function have to do with the Gaussian space, with the analysis on the hypercube, right? What does this have to do with the hypercube? There is a proof of the isoperimetric inequality on Gaussian space that goes through the sort of isoperimetric inequality on the hypercube, and it works. It was discovered by Bobkov in the 90s, and it works by this inequality called Bobkov's inequality. So, and this illustrates an important principle that we're going to use later. So let's take a look at this inequality. So Bobkov's inequality is a functional inequality that is valid for all functions on the hypercube that take values in the interval from 0 to 1, not just the 2 points 0 and 1. And it takes this shape. And the interesting thing about this theorem is that it can be proved just by induction on n. So if we put in n equals 1, then the only two variables in this problem are essentially the values that f takes on 0 and the value that f takes on 1. So it becomes a simple inequality in two real variables. And if you can verify that inequality in two real variables, then there's an induction argument that you can run that shows that it must also hold for all n. And then you can extend this argument via some central limit arguments to give the Gaussian isoperimetric inequality. And so what does this have to do with the isoperimetric inequalities from the beginning? If I plug in the characteristic function of a subset, then what I get is exactly an isoperimetric inequality, except it is now one that takes into account the boundary measure. It takes into account the edges weighted with some power. Okay, so you have a power of 1/2 coming out here.
Where did we get 1/2?
So the gradient of the indicator function is defined as the sum of squares over the coordinates.
Good.
And this inequality is not sharp, and I'm looking for sharpening this inequality. So before we talk more about how to sharpen this inequality, I want to take a step back and make it a little bit more general. So we have been talking about these quantities, expectation of HA to the beta for different beta. So to convince you of that, let's plug in beta equals 0, we get the vertex boundary measure. So HA is 0 if x is not a boundary point. And if we plug in beta equals 1, we get exactly the total count of edges. And if we plug in beta equals 1/2, we get this funny inequality of Bobkov that we saw. And it also came up in an earlier paper of Talagrand, who basically first noticed that if we compute this quantity with an exponent beta equals 1/2, we can prove some lower bounds that are independent of the dimension n. And that's a really remarkable result. So why is that a remarkable result? Because we can plug in examples. So let's plug in the Hamming ball example from before. So the hummingbird example is a particularly simple one because for each boundary vertex we have exactly the same number of edges that point to the outside, right? So if you exactly have n divided by 2, say n is even, many bits that are equal to 1, then you just flip one of them, one of the zeros to 1, and then you're outside, right? So, and there's exactly n half many ways to do that if half of the bits are 1. So what you can get is that EHA to the beta for hummingbirds that are roughly half the volume is roughly n to the minus 1/2 plus beta. And so if beta is anything less than 1/2, then this will go to 0 again. So beta equals 1/2 is exactly the interesting point where there's a possibility that it might not go to 0, that there might be a lower bound that's non-trivial and uniform in n. And this is indeed the case. And now what I want to know is exactly what is the answer to the minimization problem. So given some beta between 1/2 and 1, what is the best value b beta of volume of A such that this inequality holds? So in other words, what is the value of the beta isoperimetric profile? Okay, so I fix my volume and I want to minimize this beta weighted boundary measure. So if we compute it again on our familiar example of a codimension k cube, then what we see is exactly the expectation of HA to the beta is equal to 2 to the minus k times k to the beta, and rewritten in the variable of the volume, this is exactly this logarithmic function now with the power of beta. And the conjecture is that this is sharp when it can be sharp. So the conjecture is that for all beta greater or equal to 1/2 and all codimensions, the value of the isoperimetric profile is exactly the value given by the codimension k cube. And this is known now due to our work with Durcik and P Ivanisvili for all beta greater or equal to 0.50057. So we couldn't quite get it down to 0.5. But it's not. One could hope that it's not far from here. Unfortunately, I have no idea how to get any further to 1/2. Otherwise, I would have done it. So, okay. So let's look a little bit at the state of the art for this problem and the history. So I made this table here. So in the 60s and 70s, people were looking at beta equals 1. This is really the most natural case to look at, and the problem was exhaustively solved. Nowadays, there are still very interesting questions about stability and about the case of p-biased cubes that a lot of people study. And then Kahn and Park in 2020 came up with this very nice paper where for the special value of beta equals binary log of 3/2, which is exactly 0.58, they showed that the isoperimetric profile satisfies this lower bound here. And this is sharp if you're looking at a half cube or a quarter cube. Sharp in the sense that you get the same number. And then later, Beltran, Ivanisvili, and Madrid extended this to all subcubes. Not just half and quarter cube, but all the subcubes. And in the same paper, they were also able to get a lower bound that is sharp only for the half cube. And then in our paper, we are trying to get as close as possible to 1/2, and we can manage to do that for all subcubes. So what is this lower bound? So I've always written down here what's the lower bound that all these papers prove. So here we see this logarithmic function, here we see this other function that's also very natural for other reasons. This is again from the subcube example, and this is some cubic interpolation polynomial. It's also very natural to consider. Now what is this lower bound that we are proving? It's some horrendous and ugly function, but I'm going to try to convince you that it is somewhat natural still. So this function is piecewise defined. For x between 0 and 1/4, we're going to take this logarithm. For x between 1/4 and 1/2, we're going to cubically interpolate. that this works is somehow a miracle. And then from x equals 1/2 to 1, we're going to take this interesting rescaling of the Gaussian isoperimetric profile. And this, yes?
So do you conjecture that these lexicographic balls are sharp for...
This is an excellent question. No, this is not true, I think. I'm pretty sure
so
that's not
something
true.
about powers of 2 then.
Yeah, I don't know what the answer is for the, so what are the extremizers for beta away from 1? So I have no idea. And they don't seem to be the ones given by lexicographic order unless it's a subcube.
Yeah, so in the table you have one value of beta, but you claim all betas which are at least this value, so you can deduce a result for all.
Yeah, that's right. So these results get better as beta goes closer to 1/2. Yeah, so the smaller you can make beta.
You mentioned, at least in some of the results, that they are tight.
Yes.
So you know what the optimal set is, at least in those.
Yes, for subcubes. So all these results are tight for subcubes. That's what we were aiming for. So, if you can't make it tight for all subcubes, then at least for half cubes. But these results are, so this inequality is sharp for all subcubes. And you can see this because all subcubes fall already into this first part of the function. But I have no reason to suspect that those two parts are sharp, but they are somehow sharp for this argument, as we will see. Okay, so what's the state of, so what I've told you about here is the history for values beta greater than 1/2. So now I want to tell you about the history for beta equals to 1/2. So this whole story was started by Tyler Grant in this landmark paper, and he proved a lot of bounds. He was also especially interested in the p-biased case, but we only look at uniform measures here because we already don't know how to answer that. For the 1/2 isoperimetric profile, it's the most elusive one, that's the hardest one to crack. He proved this lower bound. He wasn't interested in the multiplicative constant, this is what he got. And then Bobkov and Goetze improved this square root of 2 to square root of 3, giving the numerical value 0.43 if you plug in 1/2. What we want to get to is 0.5, right? So Beltran, Ivanisvili, and Madrid got to 0.45, and you notice that all these lower bounds are of this shape, constant times x times 1 minus x, and there's actually a barrier to how good can this get on the half cube, because you can plug in the quarter cube, and if this constant is any bigger than 4 times square root 2 over 3, then you're going to violate the quarter cube example. So you can never achieve something better than 0.47. What we can get with our bound is to 0.4985, which is really close to 0.5, but it's not quite there, and it's not clear at all how to make it the rest of the way. So, and you'll notice that I've inserted this constant here, 0.997, so the dream would be that this function is actually a lower bound, but it's not. And it's a simple observation shows that if you have some function that's not quite working, you can always multiply it by a constant smaller than 1. There's always some constant that's going to work for you. And since this function almost works, that constant is really, really close to 1. That's basically the story. Let's draw a picture.
So it's not correct that capital B 1/2 is greater than little b 1/2, or you don't know?
Yeah, that is not correct. That is, okay, that's a great question. I do not know whether that is, I don't know that, yeah. It might be correct. It might be correct. Don't know that. So let's look at this as a picture. So now I'm not only looking at x equals 0.5, but I'm looking at all the values of x. And I'm just plotting here this Talagrand function and the other functions and then our function. And later we're going to see this picture again. Well, how much time do I have left? I don't think I have so much time left. So this part about Poincaré inequalities
you have half an hour, so it's
so basically this is, I'm only mentioning this because this is the question that Pata originally asked us. So this is where we started working on this. And we can also say something about this question essentially because Poincaré inequalities are basically like isoperimetric inequalities. So the gradient just becomes a way to identify the boundary, and the expectation of the gradient to the p is then like this beta power of the edge counting function, except that p corresponds to beta divided by 2. Or 2 times beta, I should say. So yeah, you can just apply this and you get some other results. So here, what you want to do is you want to get as close as possible to 1, and we cannot quite get there, but we can get to 1.00114 for a sharp constant. Okay, so I'm going to skip that. Now let me talk about a major ingredient of the proof. And also some other results along the way. So let's go back to this, this theorem of Bobkov, right? So this is Bobkov's inequality. This is very well known in the analysis of Gaussian functions. And as we saw, it also has a direct implication for an isoperimetric inequality on the Hamming cube. So it's very natural to start with this, but the problem was that, if you remember that inequality, it had both sides in it. So if I can go back to that inequality, oh god, so many slides. Okay, here. So this is not quite the kind of isoperimetric inequality that we want, because it's mentioning the expectation of HA square root and also the expectation of HA complement square root. And these two are not the same if the power is not 1. If the power is 1, they are the same, but if not, they are not the same. And so this is a problem. Let's see how to deal with that. So I said before that the remarkable thing about this inequality is that you really only need to check it for n equals 1, and then it automatically holds for all n by an inductive argument. So what is the case n equals 1? It's this horrible inequality. Now, I want to generalize this. So I want to generalize this in 3 different ways. First, I'm going to replace the interval 0, 1 by any interval. That's important. And then I'm going to replace this 2 norm here by any norm. That's also important. And then I'm going to also replace this gradient by any sort of sublinear operator that's nice enough. Okay? That's also important. So I have these kinds of inequalities, and they hold under some mild conditions on the norm and on this sublinear operator. Basically, you can run the same inductive argument and you can extract what you need, and then those are your assumptions, and they're quite mild. They work for a lot of interesting cases. So particularly, this is the case that that gives us a one-sided isoperimetric inequality, where we no longer take simply the absolute value of the difference of f of x and f of x plus ei, but we now care about the sign. So we care about whether we're going outside of the set or coming inside the set. So we're only going to take one side of that, and then this two-sided two-point inequality becomes a one-sided two-point inequality. And instead of using the 2 norm, we can use the beta norm, and it works, okay? So now the question becomes, also if we plug in the whole interval, then we get exactly an isoperimetric inequality of the shape we want. So now the question becomes, how do we hunt down such functions, right? So the isoperimetric profile, the Gaussian isoperimetric profile is a natural one to try. And it doesn't quite work, but you can somehow multiply it by constants, and then it somehow works, but it's very far from optimal. So how do you make functions here that actually achieve equality on subcubes is the interesting part. It's not so super hard to get some function that satisfies this, but to get a function that actually achieves equality. Okay. So what do I have here? I see. Okay, so what Bobkov did in his 90s paper was basically, so this is the most technical part of his paper, where he proves that if you have this interesting second-order differential equation, that's exactly the differential equation satisfied by the Gaussian isoperimetric profile, right? This composition of the a distribution function and the cumulative distribution function's inverse up to a normalization, then you have this inequality. This is a remarkable statement because somehow it goes from a local statement, this differential equation, to a global inequality. It's not at all obvious how to do that. And this inequality is just not the kind of inequality we need. So can we get such an inequality for the one-sided B? And the unfortunate answer is no, you cannot. At least not with the same assumptions. You need one additional assumption. So you need that the derivative of B is smaller or equal to 0. And so what's an example of such a function? It turns out that if you rescale and reflect the Gaussian isoperimetric profile, then it satisfies this condition. And so what is this notion, what is this number W? So this number W is computed such that the value at 1/2 is exactly 1/2, right? So we're trying to dream, we're trying to see if we can make a function coming from the isoperimetric profile that will give us equality, okay? And so we're just rescaling the isoperimetric profile, it satisfies this inequality, and we know exactly how it looks, right? It's first increasing, then it's decreasing, and so we just have to take the part that is decreasing to satisfy this inequality, and we can rescale it for free, leaving this equation invariant, and we just take the rescaling that gives us the value 1/2, okay? It's just some number, W, okay? It's an important number. And then you have this inequality on some interval. Okay, but that's useless. That's completely useless because what we need to get an isoperimetric inequality is a function that has values in 0, 1 in the complete interval. It doesn't help if it only satisfies it in a partial interval. So that is one problem. But that problem can somehow be fixed by using other functions. So another problem is that x0 is not quite at 1/2. And that can be fixed by introducing a power of beta. So if we take betas bigger than 1/2, we are basically making this inequality easier to satisfy, right? So we're increasing the right-hand side, and so it barely fails around 1/2. So if you increase beta a little bit, then it will hold on from 1/2 to 1. And it turns out that this is the number you get. This is roughly 0.50057. Okay, so I said before that if you have an inequality that a two-point inequality that doesn't hold on the whole interval, then it's useless, right? That's actually not quite true. You can rescale indicator functions to have values in the correct interval, and what you get is a very, very disappointing inequality, but it will be good near some point. So if you take the inequality from before, if you take the function from before and you rescale the indicator function to take values in this interval and you plug it into this inequality and you run the inductive argument, then you get a very nice corollary, which is that the expectation of square root of HA, that's a quantity that's hard to bound from below, right, satisfies this inequality. This is a mouthful, this doesn't mean anything, right? So let me explain what this means. This is a terrible estimate if A has any volume far away from 1. But as A approaches 1, this is actually the best bound that I'm aware of. So it's better than all the other bounds that came before. And asymptotically, this thing as A goes to 1 is equivalent to some log function with the constant square root of 2. And so there are some questions here. Is this constant here sharp? But actually I have an even more basic question, which is this power of log sharp? So I don't even have a reason to believe that this power of log is sharp at A equals 1. I would be very interested if somebody can find out what is the sharp power of log as the volume goes to 1. So this is the asymptotic case as the volume of sets goes to 1. What about the asymptotic case as the volume of sets goes to 0? we can also do a similar trick, rescaling indicator functions and applying a two-point inequality, and we can derive this lower bound here. This looks very close to the dream. The dream is if there's no 2 here and no minus, right? So the 2 actually helps us make this bigger, right? But the minus doesn't help us at all, okay? The minus is very bad. Unless the volume of A is tiny, then this minus tiny A doesn't make any difference. And asymptotically, this is really the dream function, right? So asymptotically, this is completely sharp, including not just the power of log, Talleyrand already had that, but also the constant. That's the point of this inequality, okay? So this is completely sharp asymptotically as A goes to 0. Yeah, so much for the asymptotic stuff. That's sort of easy. We are only looking for things that are asymptotically sharp. But now let me tell you about how to get this global inequality that works for all volumes. So what we need is really, we need to step away from this Bobkov regime of trying to improve Bobkov's inequality. It doesn't quite seem to work. And maybe it's not supposed to work because in the Bobkov inequality we're always trying to prove these functional isoperimetric inequalities for functions that take values in the whole interval, right? But what we really want is just binary valued inequalities for functions that are just binary valued. So maybe we should make use of that fact that they're binary valued in the induction argument, right? And so that's exactly what Kahn and Park did. So Kahn and Park came up with a new inductive argument that the upshot of which can be formulated like this, where you have another two-point inequality. So this is like the inequality from before by Bobkov, but it's a bit more complicated, mainly by introducing this new term here in the max, right? So if you drop this term here, then it's exactly the Bobkov style two-point inequality. But we're making this a bit harder to satisfy by introducing this other term here. So if this inequality holds, then one can again run an inductive argument. And once you have the plan to run this inductive argument, and once you've written down this inequality, it's actually automatic to prove it. So you will be able to prove it. You just use Jensen's inequality at one very, very key step, and then you'll be able to prove it. The upshot is that the isoperimetric inequality will be greater or equal to any function b that satisfies such an inequality. Okay? And this is a horrible looking inequality, right? So, okay. I will not talk much about the proof. So what can you do? You can test, you can take your favorite function, you can test inequality. Does it work, right? And again, I want to stress, it's not terribly hard to find functions that satisfy this inequality. It's hard to find functions that satisfy the inequality and give you the sharp value at, say, 1/2 or 1/4 and so on. We can test our favorite functions like 2x times 1 minus x. This is what Kahn and Park did in their original paper. This is like the first thing to try, and this worked, but it only worked at not the dream exponent of 1/2, but at this funny exponent, and this is short for that function. You cannot go below this. So this is how they got their sharp result at 1/2 and 1/4. And the main technical work for us will be to convince ourselves to prove that the two-point inequality holds for this absurdly defined function, right? So at this particular exponent, right? But actually, before we prove that, we should ask ourselves a different question. How does one come up with these functions, right? So how does one find a good large function that satisfies this Kahn and Park two-point inequality, right? And so, and this is one of the novelties, of the main novelties of this paper, I think, which is, so okay, let's start out by very simple observation. So if B1 and B2 satisfy this inequality, you can always take a max, and now you have a better function that satisfies the inequality. You can also do this with any family, and you take a soup. And so this means that there's a well-defined largest function that satisfies the inequality, right? And we can give this thing a name. We can call it the envelope function. This is a well-defined function, and this function is not defined on the unit interval because it can only be defined for, or it actually makes sense to restrict it to only dyadic rationals, because those are the only numbers that can come up as volumes of subcubes, of subsets of the hypercube. So what we know from the argument is we have this function, this is this largest function. We know that our isoperimetric profile, the dream function we're looking for, is greater or equal to this envelope function, right? What about the reverse, right? We don't know. Actually, if beta equals 1, the reverse is also true, this is an equality. For any other value of beta, I have no reason to expect that this would be an equality, except at subcubes. So that's something you can see from the proof. And this is also why our work doesn't give much information on the case of not being a subcube. So we don't have any clue on what the extremizers might be if you're not looking at volumes that could be the volume of a subcube. Okay? So, and this function, obviously, isoperimetric profile is very hard to compute, right? So even if you restrict your attention to a dimension n, then you have 2 to the n, so double exponential number of subsets to check, right? By brute force. And it is hard to cut this down significantly. What about this envelope function? It's much easier to compute, actually. You can almost save a whole exponential. So how to compute this? Well, very naively, I restrict myself to bit strings of length n, and then I get this sequence of partial envelope functions, and they converge very naturally, monotonously to some function, and I'm just going to call that the envelope function. I can prove that this actually converges. I don't know how fast it converges, but it does converge. It's not difficult. And now these can be computed by some greedy approach, as one can imagine. I'm not going to talk about that much more. And so this allows us to draw pictures. And so for any given beta, I can now plot what is the envelope. So what is the best function that satisfies the two-point inequality. And let's do this for beta equals 1. And we recover exactly the isoperimetric profile for beta equals 1 that's known, right? So we had this plot before. Now this is the same function computed using a totally different method. Takes a lot more computation. But you end up with the same exact result. They are equal. So that's promising. It's probably doing something correct. Now what at beta equals 1/2, we get this green curve. That's the beautiful function we are looking for. We have no idea what it is. But we can get very close to it. And then here's the Kahn-Park function. I'm calling it Kahn-Park function because it's this exponent that they were looking at. But nobody knows also what the shape of this function is. And I can, of course, also compute it for any beta in between, and I get this beautiful fractal transition, and some interesting things happen here, right? So at some value of beta, somehow there's an interesting transition from fractal to smooth type behavior on the right. Maybe it's just an artifact, maybe it really is there, I don't know. So there are some interesting things to explore here.
But do you know that this envelope equals a profile?
No, I don't. But I know that it does at beta equals 1, and I conjecture that it equals it at subcube volumes, right? I don't know about other volumes. I don't know. Okay, so now let's look at the picture from before. At beta equals 1/2, what are the bounds for the isoperimetric profile, right? So the blue one is the Tanner-Grant, and then two others, and then the red one is ours, right? So how close is this to the best possible thing we could get using the envelope? If you compute the envelope, you get almost the same plot. It's the same exact function. And that's how the order of steps in coming up with this was first to compute numerically this envelope, and then start looking for the shape of the function. And that's how it looks so funny, because you're trying to adapt using functions that you know to this profile, right? So you're computing numerical derivatives and so on, and you somehow realize that it should be that, exactly that piecewise defined function. No other function is that close to the, no other function that we can think of is that close to the envelope. But perhaps you could do better. There's an error. This is the error. So you'll notice that this error here is not even tight. It's not even tight at subcubes. That's because I'm looking at exponent beta equals 1/2. If I make the exponent a bit larger, then we can actually bring these down to 0. But these spikes here are very interesting. They would be nice to get rid of. And then also this curve here. I have no idea what this error is, where it comes from, but it's strikingly close to the envelope, the function that we have. So this is numerically computed, right? It doesn't tell us anything. So now basically what do we have to do, right? So we have to prove the two-point inequality. So I have a few more minutes. Let me explain again. Let me summarize. So this is basically the two-point inequality with the right-hand side subtracted. Okay, so what I want to show is that this function here of x and y is greater or equal to 0, right? It's not negative. And what is the function that I want to plug in? I'm going to plug in this funny function. So I'm going to plug in this piecewise defined function here for capital B everywhere. So now all I need to do is that this is a definitive function for two definitive variables x and y between 0 and 1. Beta is also a given number. And so you could think that, oh, this is a calculus exercise. I can give this to my calculus students. But they're going to struggle because this is actually quite difficult. So already the two-point inequality by Bobkov was quite tricky to prove. And it has a much more elegant shape with a lot of symmetry in it that you can try to exploit. There's much less of that symmetry happening here, right? This is a completely chaotic thing. So what we have to do is prove this. And so maybe another point that I want to make in this talk is that you can make your life a little bit simple. So of course we all know the usual tricks that one can go and use here. One can take derivatives, discover convexity somewhere, one can change variables, one can do all these tricks, right? And but have fun with this, right? There's always going to be some cases that you're not going to be able to very easily do with these tricks, and a hint towards that is that there is this exponent beta. It's a very, very specific number. We don't know why it is this number. It's just this number, right? And so if you change this to a slightly smaller number, it's going to fail. The inequality is going to fail. And since we don't understand why this number, there's no way we could get an intuitive proof of this, right? So, because it's very, very tight. Anyways, so what do you have to do? Well, this is piecewise defined, so you do a case distinction. It's very, very boring, right? So yeah, you just look at all these cases. These are the lines x and y equal 1/2 and 1/4. That's where the piecewise distinction happens. And then where also x plus y divided by 2 equals 1/2 and 1/4, and you get all this division here. Let me just point out two particular ones. So in this upper right triangle, this is the Bobkov type case. So this is as far as Bobkov will take us. And notice it doesn't take us quite to 1/2. And this is actually, this little region here between 1/2 and x0, this is exactly where the interesting stuff happens that we don't understand. So this is exactly where our dream function, this function j, a rescaling of the Gaussian isoperimetric profile, fails to satisfy this natural analog of Bobkov's two-point inequality. And we have no idea why that is the case. But you can so here's exponent 1/2. It satisfies it up to here using a Bobkov style argument. And then it just fails. So this is sharp here. It stops working here because this is where this function j achieves its maximum at x0. So this is where this derivative condition fails. But you raise the power a little bit larger, you make this a little bit easier to satisfy, and then you can push it to 1/2. So that's the story of where beta, this funny value of beta comes in, right? Okay, let me look at another case. So if we look at this case, then we have a function j appearing, we have a function logarithm appearing, and we have some weird cubic polynomial parametrized appearing. So what we need to prove is that this inequality holds here in this region here. And this is not a critical region. It's not a region where we're close to failing. So there's many, many ways of how to do this manually, but it's tedious, right? It's not easy. Okay, so we do have to consider all these cases, but in many of these cases we can actually dramatically simplify our work by letting the computer do a lot of it. So, for example, here is one very critical case where x is equal to 1/2, right? Then we have a function of a single variable y, so I can just plot it, and notice the scale of the y-axis very close to 0, so you have to be very, very careful. And this is 0 here at y equals 0, at y equals 1/2. And then it has an interesting shape, right? It's not monotone. We do not know where it achieves this local minimum. And this value of this local minimum is very, very close to 0, right? And so if we plug in this value for beta, with this funny binary here, it's very natural to work with these because these are floating point numbers. They can be represented exactly in the computer without further trouble. If you just change this 19 to 18, you're making it a little bit smaller, then it crosses the y-axis, okay? And obviously you could expand, so there is some natural, just by intermediate value considerations, there's some value of beta that is exactly going to make this 0, right? Make it touch. And you can compute as many binary digits of that as you want, and then that can give you more digits of this magical number 0.50057 if you like, but we just decided to stop there. So let me now show you how a computer, so I'm claiming you don't need to work at all to prove this inequality. Okay, I'm lying, but you need to work a little bit, but you don't need to work much more than you might think to prove such an inequality that this is greater than 0. As long as it's true, the computer can actually do a lot of that for you. And here's just a small toy example of how that can be done. So let's consider a function with single variable, right? Just like the one before, with some funny terms that we might have to work a bit to understand how they cancel out each other, right? And it's very close to 0, right? So anything trivial, like using monotonicity of all these components directly on this full interval, will fail, right? Because there's some subtle cancellation that makes it not quite 0 here at this point, okay? So I have to, but it's greater than 0. You can plot it, you can see it, you can hand in this plot of Mathematica as a solution to your homework, right? If you're a student, and then you will get 0 marks because that is not a proof, right? So how does one make this a proof? And this is essentially automatic, so there's nothing much one has to do. So it is actually, should be considered a proof almost, because you can use interval arithmetic. So I'm going to introduce this concept called a tight lower bound. How many minutes do I have left?
5.
Okay, so what is a tight lower bound? I'm going to introduce a function that lives on intervals instead of functions, and I'm going to say that it is a tight lower bound if it is a lower bound for all whenever x is contained in that interval, okay? And as the interval size shrinks to 0, this bound becomes sharp, okay? That's what I mean by a tight lower bound. And that's exactly what you get if you if you use monotonicity in all these components, right? Then you get a tight lower bound for such a function. So the idea is to not use it on the whole interval, but to just use it on a partition. And so here's a trivial observation. The observation is that if you have a partition of your whole interval where you're trying to prove greater 0, and you can verify that for each interval in the partition, the tight lower bound is greater 0, then you have just proved that f is greater 0, right? So you have reduced this problem of evaluating infinitely many inequalities to just finitely many on the partition endpoints, okay? Once you have a tight lower bound. And the tightness actually guarantees that this is possible just by a compactness argument. And you don't even need any smoothness on f. So this is a very, very minimal technology argument, right? That's all we need is some kind of semi-continuity. And there's a simple algorithm to find it. You can just bisect, dyadic bisection. You try the whole interval, doesn't work. Then split it into 2 and go on, right? And you will find, guaranteed, you will find a partition that works if the statement is true, okay? once you have a partition, you just check, you just evaluate, right? So how do we get a tight lower bound? It's very, very simple. You just do, you just use monotonicity of the functions that make up your given function. And recursive bisection gives me now a partition of 29 intervals. So the calculus student should really hand in this as a solution, right? This is basically that, if you take that picture and you make it, you try to make it a proof, then this is the proof. And this can be done by a computer. You don't need a human to do this, right? You're done here, and of course there are issues, right? We are worried very, very quickly. So let me point out the most obvious one. We need strict equality for this one to work. We need a tight lower bound, but that's somehow not a big deal. You can get it. And then another problem, if you are lazy in making the tight lower bound, you just use monotonicity a bit too greedily, then maybe this partition exists, but maybe it's beyond machine precision. Maybe those partition sizes maybe it's a too large partition to store in the computer, maybe the intervals are too small, so you run into issues of making this practical. And then there is also another big problem which you're all going to think of, which is, can we actually trust computer evaluations of functions at given points, right? And of course, the answer is no. We can absolutely not trust the computer to evaluate functions, at least not if we do it naively. But there is luckily a way to fix that. There's a way to do numerical evaluations on the computer rigorously, that they have they count as mathematical proofs. So why can we not trust computer evaluations? Because there's two kinds of errors that can be introduced. One is from floating point arithmetic. The computer doesn't know real numbers, it only knows floating point numbers. This is a very small finite subsets of the dyadic rationals. Then also there are numerical errors by the computer not knowing what is an exponential function, but instead it has to use a Taylor series. So you have to control both of these sources of errors, and this can be done. So let me just show it. Let me just finish with one example. Due to Rum from the 80s that really clearly shows you that you cannot just trust an evaluation of Mathematica. So let's take here, this is, okay, it's not quite a polynomial, but it's a function of two variables, rational function, right, with moderately sized coefficients. You would think that this is going to be no problem, right? And we're just going to evaluate this at two values of A and B, right? Also moderately sized values. Mathematica tells me after I enter this number, -1 times 10 to the 21, huge, right? At the negative side. And this is what Mathematica gives me without any warnings, but one has to keep in mind the default settings are just double precision floating point arithmetic. And if one is a little bit careful, one sees that the correct value is actually orders of magnitude away from this. So it's not even close, it's not even in the right ballpark. And naively, you might have not guessed that this could happen because all these numbers are moderately small, right? But what happens here is that there's some dramatic cancellation with floating point numbers that causes the result just to be completely wrong, okay? But this can be fixed by not computing with single floating point numbers, but instead computing with intervals. And keeping in mind the rounding rules of IEEE 754, and you can automatically track the error in each step by using interval arithmetic. And in that way, you can produce a program with the property that as long as you trust both the hardware, which we trust because we trust that it implements IEEE 754, of course that can be debated also, but let's just pretend we live in a perfect world where that protocol is implemented perfectly. And then we also trust the software implementation. Then this is actually, the computer can produce proofs that the output of some computation lies in some interval of two specific floating point numbers. And this has been done over the last few decades in many influential projects. So one big one was the proof of the existence of the Lorentz attractor by Tucker. And then another one is also the sphere packing problem in 3D, right? That also involved a lot of computer systems. And nowadays there are open source libraries that do this. And open source, I cannot over stress how important that is, because we want to go back into the source code and actually see, is this error correctly computed, right? And we can do that, and it's not hard to verify this. It's just a few lines of code, as long as we believe that the hardware is correct and the compiler works correctly. We can verify this, that this works correctly. And so you can produce proofs. Okay, this is all I wanted to say. Thank you.